Welcome to an in-depth exploration of dynamic vectors, the foundation of resizable arrays in modern programming. A dynamic vector is a resizable array that grows and shrinks during program execution, adapting to your data needs. Let's first understand why we need dynamic vectors by examining the limitations of static arrays. Static arrays have a fixed size determined at compile time. Once created with 5 slots, you cannot add a 6th element. The fundamental problem is that static arrays cannot grow. Their size is fixed when created and cannot change. But real applications need flexibility: uploading unknown numbers of photos, reading files of unknown length, processing streaming data. The breakthrough idea is separating two concepts: how many elements we have versus how much space we allocated. We maintain two values. Length is 4 elements actually stored, while capacity is 8 total slots allocated. This gives us room to grow. The invariant is simple. Length is always less than or equal to capacity. The magic of dynamic vectors lies in their growth strategy when capacity is full. A naive approach is growing by 1 each time, but this is disastrous for performance. Growing by 1 means push 1 copies 0, push 2 copies 1, push 3 copies 2, push 4 copies 3. That's quadratic time complexity. The smart approach is doubling capacity each time we run out of space. Doubling gives capacity progression: 1, 2, 4, 8, 16. Each doubling happens less frequently as the vector grows. This doubling strategy achieves amortized constant time. On average, each push takes constant time. Let's break down what happens when you push a new element into a dynamic vector. First, we check if length equals capacity. If so, we need to grow before inserting. When the vector is full, with length equal to capacity, we cannot insert directly. We must grow first. We allocate a new block of memory with double the current capacity. The old memory has capacity 4, the new memory has capacity 8. Now we need to copy the data. We copy all existing elements from the old memory to the new memory location. After copying, we free the old memory block to prevent memory leaks. Finally, with room available in the new memory, we insert the new element at the end. Understanding where the vector lives in memory is crucial. The vector struct itself lives on the stack with just 3 fields: pointer, length, and capacity. The pointer points to the actual data on the heap. The stack holds the small metadata structure, while the heap holds the potentially large array of elements. Let's analyze the time complexity of vector operations mathematically. Accessing an element by index is constant time, just like regular arrays. In the worst case, push takes linear time when we must copy all n elements during growth. But amortized over many pushes, each push takes constant time on average. The total copies for n pushes is the geometric series 1 plus 2 plus 4 plus 8, which sums to n-1, less than n. Dividing by n pushes gives average of 1 copy per push, which is constant time. When a vector goes out of scope, we must properly clean up to avoid memory leaks. Without proper cleanup, when the vector is dropped, the heap memory remains allocated but unreachable. When the vector is destroyed but the heap memory isn't freed, we have a memory leak. The solution is implementing the drop trait to properly deallocate heap memory when the vector is destroyed. We must drop each individual element first to run their destructors, then free the array memory. Let's summarize the key concepts of dynamic vectors. The core insight is separating length from capacity, giving room to grow without immediate reallocation. Doubling capacity each time achieves amortized constant time pushes despite occasional expensive copies. The small metadata structure on the stack points to the large data array on the heap. With manual memory management, we must carefully free all allocated memory to prevent leaks. The beautiful result is constant time amortized performance for the most common operation, push.